Hey everybody, this is Joni Overly and we are in our final project for our team teach. So let me get started and introduce to you my teammates.
I'm Amanda Pennington.
Calie Plummer.
Gabby Guest.
Cheyenne McDorman.
And this is our team and we are ready to go. Rock on!
So we're going to start with our questions from lesson 1, started with Gabby.
Okay, so in this example, we need to show and explain a graph to correlate with the function of the amount of gas in a gas tank when a driver refills the tank on a drive across country. So we're just going to create a gas to represent us filling the tank and what it's going to look like when the tank is going across country and decreasing. So on the left, it shows the amount of gas that is being put in the tank, and the bottom correlates to the distance. So as it's going up into a straight line, it's just representing the gas that is filled into the tank. It's a fully filled tank. And then the line going down is just explaining that it's decreasing as the distance goes on.
Great job.
Okay, so this one, it says, show and explain a graph to correlate with the function of the height of an elevator stopping at each floor on the way up. So the left is going to represent floors, and then the bottom is going to represent the amount of time it takes. So it's just going to look like almost stair steps. So as it gets to a level, it stops, and then it goes up a level, and then it stops again, it goes up a level, and then it stops again. So that's just how you're going to explain kind of like the elevator stopping at each floor on the way up.
Okay, so Gabby, so when it goes up like a step, that means one floor is going to be taken?
Yes, exactly. So as one floor is taken, it'll be just a straight line, which is what that represents, and then the other line next to it is just represents that it's stopping at that point for a while.
Oh, okay, thank you.
You're welcome.
So the time down here would really be time stopped, because when you're rising, the time is staying consistent, and then when it's stopped.
Exactly. So the floors kind of represents it going up, and then the time is just the steady line.
Okay.
So next it says, show and explain a graph to correlate with the function of the height of a bouncing ball dropped from a table. So this one is also pretty self-explanatory. So the left represents the height and bounces, and then the bottom represents how many bounces that it's going to take. So if you were to drop a ball, it's just going to go up and down until the ball stops. And at the end, you can see it's at a steady line. So that's when it represents how the ball stops, and that is how you explain this example.
Great
So
job.
that's why it gets smaller every time, because as the ball bounces, it loses its momentum until it just gradually just kind of rolls away.
Exactly. So that's exactly what you said. This example, we want to show and explain a graph to correlate with the function of the length of a shadow of a flagpole through a sunny day. So this is just going to represent a shadow. So on the left, it's the length of the shadow, and the bottom is just the time it takes. So it's just going to look almost like a reflection, like it's flipping over, because a shadow reflects the same exact figure, just kind of backwards. So that's why it looks like that.
Okay. So this would be like the peak time of the day when shadows are out.
Yes, exactly. So whenever the sun hits it and there's a shadow, then that's what it'll look like.
Okay.
Great job.
Thank you.
You're welcome.
So in this question, we are going to talk about functions. And so it's really easy for me to think about functions as kind of a machine. You take your x variable, which would be here, and you put it into the g function machine. And so it will come out looking like this function, g of x. And so whatever the x variable would be, it becomes g of x. And so when you would have your g of x and it would go into the f function machine, it becomes f of g of x. Sometimes written fog of x, or this way here. And so whatever your answer you would get for your g of x equation would become your input for your f equation. And so, but it's written as f of g of x.
Okay. So, Calie, so when it shows that you're putting the x in the g function, it becomes g of x. And when it's sending it to the f function, it becomes d of x of f.
Right, it becomes f of g of x. So this is g of x, and then we're taking f of g of x. And so your g of x, whatever your answer is going to be for that one, becomes essentially your x variable for the f function. So it's just whatever number you're going to put into the f function is the answer from your g function.
Thank you. I understand that now.
And so when we look at these, we see we have our original x variables here as 0, 1, 2, and 3. And then we have our f of x function, which is a 3 multiplier, which just means whatever x is, which are these numbers, we're multiplying by 3. And then our g function is our add 8 function, which means whatever our answer for our f of x function is, we're going to add 8 to it. So if your x was 0, when you multiply 0 by 3, it's obviously 0. And then when you add 8, it becomes 8. And the same for 1. You multiply it by 3, and you get 3. And then when you add 8, you get 11. And you'll do the same thing for 2 and 3. And so if you were to graph them, when you would graph your initial f of x function, which is our points are going to be 0, 3, 6, and 9. You can see them here. You're going to add 3 to them. Or I'm sorry, add 8. And so our g of f of x line is going to be 8 points from our 3 multiplier function, our f function.
Great. Hey, Calie, let me ask you a question. So like on when x is 0 and f of x, and you plug it in, say if your number was 10 over there on the g of f of x.
So if it was x plus 10?
Okay, yeah. What would that be?
So if it was x plus 10, and we can use 0 for an example, if your x is 0, and then you plug it into your 3 of x function, it's still 0 because 3 times 0 is 0, then you're going to add 10 instead of 8. So this answer would be 10. And so just for every one that you would do, instead of this being an add 8 function, it would be an add 10. So on your graph, it will correlate to, it would be 10 points up instead of 8 points up.
Okay, thank you.
Mm-hmm.
In this problem, we're going to be talking about the slope. And the formula we're going to be using is y2 minus y1 over x2 minus x1. So the function that we are looking at goes up 4 and over 2. So when we're plugging in to find the slope, it's going to be 5 minus 1 over 5 minus 3, which will give us 4 over 2, which will give us a slope of 2.
So, Cheyenne, for this problem, you're just taking the x and y coordinates from the table and plugging them in?
Yes, so y2 would be 1, and then y1, no, my bad, y2 would be 5, and y1 would be 1, and then x2 would be 3, or my bad, 5, and then x1 would be 3.
Thank
I think
you.
that's where a lot of people get tripped up, is they try and look at the first values of x and y when you really start with the second.
I agree, Calie.
Right.
That's what I try to do myself. It starts getting confusing. Yes.
Right. You just have to remember to start at the bottom or read
Right.
back.
Yes. Thank you. Good job, Cheyenne.
Yes, good job.
All right, so part B of this question, we're going to be finding the slope of this function. So we notice that it doesn't rise and it doesn't run. So we're going to take the y2, which is negative 8, and subtract it by 8 and put that over 5 minus 5, which will give us negative 16 over 0. And well, we can't divide by 0, so this function would be undefined.
So anytime you would have a 0 here, it would always be undefined.
Yes, because when you multiply something by 0, it's always going to be 0. So in this case, when you do -16 dividing by 0, you're going to get 0. So this problem would be always undefined. So anytime you have a line, straight up and down or horizontal, you're going to have an undefined function.
Oh, thank you so much for that explanation.
You're welcome. So in part C, we're going to be taking the y2, which is -4, and subtracting it. My bad.
They'll catch you.
-4. Oh my gosh. Okay. -13 and subtract that by -4. And then you're going to put that over -4 and then subtract that by -1. So it's going to be -13 minus -4, which will give us -9 over -3. And that will give us a slope of 3.
So Cheyenne, so when you have a negative number and you divide it by a negative, will it always give you a positive?
Yes, because when you multiply a negative number by a positive number, you're going to get a negative number. So same thing goes for dividing. So whenever you're dividing a negative number by a negative number, you're going to get the positive number of whatever number you get for your answer.
Thank you.
You're welcome.
All right, guys. So in this problem, we're going to be looking at x values and plugging it into the function or equation. So in the first column, we see is green, and that's just going to say x squared. So we're going to plug in the x values that we have right before that, the -2, -1, 0, 1, and 2. When we plug those in, we know -2 squared. So -2 times -2, like Cheyenne said, is going to give you a positive. So a positive 4. And we're going to plug those in, and it gives us 4, 1, 0, 1, and 4. So when we go ahead and put that in a graph, it's going to look like this. And so the origin is going to be at the 0, 0 point. And this is going to be kind of like our basis to see the future graphs, how they grow up and down on the y-axis. So right now we're going to move on to our blue. Our dark blue in the middle, our x squared plus 7. And so when we plug in our x values, the same one, for all these problems, we're going to plug in -2, -1, 0, 1, and 2, and solve the problem. We are going to get 11, 8, 7, 8, and 11. So when we plug that in on the graph as well, we see something different happen. From the green graph, we see that it's at 0. But when we look on the blue, the origin is right at 7. And so when we take x squared plus 7, that means we're going to go and start at the origin at 7 on the y-axis. So it's going up +7 on the graph. Now, we're going to look at the light blue. It says x squared minus 7. And so when we plug in our x values, we see that we get negative numbers. We got -3, -6, -7, -6, and -3. So when we pour that up on the graph, we see already that our origin is going to be down below on -7 in the y-axis. So when we have x squared minus 7, it's going to go down on the axis of the y. And then when we have +7, it's going to go up on the y-axis. So it does make a difference on our graphs, but it's still going to be on the y-axis.
Hey Amanda, when you have a function that always has x to the second power, will it always look like a u?
X squared, you can put in different variables. So you wanted to do -4, -1, 0, 1, and +4. It is still going to be looking like the parabola, which is the u. And it's going to look like that. It's just the coordinate points are going to be on a different point. But it's always going to be looking like that.
All right, thank you.
You're welcome.
And an easy way to tell that, Cheyenne, is these kind of become your points on a graph. So, you know, your origin is at 0, 0. So like this is your X value, this is your Y value for your set of points. So you would have -1 and 1, -2 and 4, 1 and 1. And you can see that they just mirror each other, like you just folded it right in half.
Okay. Thank you for giving a better estimation.
You're welcome. Okay, so in this problem, we're going to be looking at supplementary angles, similar angles, and complementary. And so we see that line 1 and line 2 are going to have two different lines going through those. And that's going to make us have all these different angles that are popping up. Okay, and first thing we need to know what a supplementary angle is. And then a supplementary angle is going to be an angle or more that add up to 180. So we know that a line equals 180, and that's going to be a key fact for us identifying the angles later on. Next, so for an example, we have 9 and 10. 9 and 10 are at the bottom, and we see that it's hard on line 2. Even though as two different angles, they're going to add up to be 180 degrees. Now, if we look at 1, 2, and 3, at the very top of line 1, we see that we get 3 different angles, but they have to add up to 180 because they're on the line. And so we have all kinds of different supplementary angles on here. Now let's move over to complementary angles. So we need to know what a complementary angle is, and that is going to be a 90-degree angle. So on this graph, we cannot take one or more angles and add them together to get 90 degrees. And so there's not going to be any on this one. But when we look at similar angles, we have quite a bit. We have 1 and 5 on line 1, and that's going to be the opposite side of the line of each other. So like 2 and 6, they're going to be the same. But see, 2 and 63, my bad, degrees. The 63 degrees is already given, so that means that the angle 2 is going to be 63 degrees as well. So it's going to be the same amount of degree. And so that is going to be that problem.
Thank you. So is the reason that there's no complementary angles is because these come in kind of on a diagonal and there's none that are
right. There's no lines coming in up and down to make that 90-degree angle. Mm-hmm. No matter how many times we try to add the different angles together to get close to 90 degrees, it just won't happen because you're right, because the lines are coming in at a tilt.
Okay, so for 2 or more to equal 90 degrees, you'd have to have at least one of these coming completely vertical.
Right, up and down.
All right, so as Amanda said, supplementary, similar angles, and congruent angles is what we're going to be talking about in this problem. So we're going to be looking at this figure. So the similar angles are going to come up as green. And then my supplementary angles are going to come up as red. And then we have our congruent angles, which are going to come out as orange. So we need to look at angle 1. Angle 1, we're going to figure this out, and we're going to look at this whole figure as one triangle. So we know that a triangle equals 180 degrees when you add up all the angles. So we're going to take 180 degrees and subtract it by 74 and 26, which will give us 80 degrees. To find angle 2, we have to look at if angle 3 is a similar angle to angle 1, and we know that a line equals 180 degrees, as Amanda said in the first problem that we looked at. We know that 180 degrees minus 80 degrees equals 100 degrees, so angle 2 would be 100 degrees. Angle 3, as we said, would be 80 degrees because if angle 2 is 100 degrees and we add 80 to it, it'll give us that 180 degrees that we need to create that line. So angle 4 is a congruent angle. And how we can tell that it is a congruent angle is that if we look at the triangle that angle 4 is centered in, we see that angle 26 is similar to that angle. So angle 4 would be 26 degrees. Angle 5 is a similar angle to angle 1. So which means that it'll be 80 degrees as well. And then we have angle 6, which is a congruent angle. If we see, as we did for angle 4, that it falls on to a triangle, the 74 falls in the same place as angle 6. So that angle would be 74 degrees. Angle 7 is a supplementary angle. And if we look at angle 8 as well, we see that it falls on a line. So we know, as in for angle 2, that 180 degrees minus 80 degrees will give us 100 degrees. So that means angle 8 would be 80 degrees.
Great job, Shania.
You're welcome for explaining.
That was a lot of angles to talk
Yes.
about.
Very much so.
I kept up because it was tough.
You did fabulous.
Yes,
Thank you.
You're welcome.
So for this one, we were asked to construct a concave polygon and then demonstrate how to find the measurements of the angles. And so this is the concave polygon that we were provided, and it is an 8-sided polygon. And so if we were going to find the sum of all the interior angles, which are these angles here, and they're labeled 3y, 7y, 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 3, 2 12s, and another 3. So all the angles on the inside, not your central angles, but these interiors. So the formula to find that is going to be n minus 2 times 180. Well, n, the letter n, is going to represent your number of sides. And so here we would do 8 minus 2, which is 6, times 180, and we get 1,080 degrees. So we know that all of these angles, when you add them together, they equal 1,080 degrees. And so since each interior angle has its own multiplier label, which means whatever we find for the y value, we're going to multiply this one by 3. We're going to add them all together to see how many y's we get that we need to divide by. So we would add them all together, and we know that they all together equal 1,080. So we would get 54y equals 1,080 degrees. And so in order to find the value of y, we would divide both sides by 54, and then we get y equals 20 degrees. So we know we will substitute in 20 degrees for each y value. And when we do that, we find that the angles that are labeled 3y, when we plug in our y value, they're 60 degrees. So each angle labeled 3y is going to be 60 degrees. And the same concept for our 7y angles, we're going to plug in our 20 degrees that we found previously for our y value. And we know that all of our 7y degree angles are going to be 140 degrees. And then our 12-degree angles, which we have 2 of, they're going to be 240 degrees apiece because 12 times 20 is 240 degrees.
Great job, Calie.
Thank you.
You're welcome.
That was a big baseball field to cover.
It actually was. That's what it reminded me of.
Yeah.
Yep.
I see a lot of bases on there.
Okay, so for this lesson, we're going to go over how to find interior, central, and exterior angles. So the first thing we need to know is the amount of sides, because it's going to be really important. So let's count out all the sides, and we see that there are 9. So let's figure out the interior angle. So first we're going to need to know the formula. So it's going to be x minus 2 multiplied by 180 divided by x. So x is the amount of sides. So we're going to take 9 minus 2, and we're going to get 7 multiplied by 180 and then divided by 9. And we get 140 degrees. Now let's go over the next set of angles. So we're going to go over how to find central and exterior angles. What we're going to do is look at the central and the exterior right here. And we need to know that we need to take 360 divided by n, which is 9. That is the amount of sides. And then you get the answer that is 40 degrees.
I'm so sorry.
So Gabby, so for the central and exterior angles,
Yes.
will you use the same method?
Do you mean like the same formula for each one?
Yes.
Sorry,
So
can you repeat your question?
yeah, you're fine. So for the central and exterior angles on how to find it, are we still going to use the 360 divided by n method?
Yes, we're going to do that for the same exact method. Exactly.
Great. Thank you so much. I appreciate it.
So the only formula, the different formula would be for interior angles has a formula all for itself, and then central and exterior share the same?
Yes, exactly. So for interior, you're going to have the x minus 2 multiplied by 180 divided by that number. And then for central and exterior, you just take 360 divided by n, which is 9.
Okay, so that's why the number of sides was so important, because that's what you divide by.
Exactly.
Okay.
Great job.
Thank you.
You're welcome.
So Joni, before you start this question, you have got to explain to me what a tetrahedron is.
So, okay, I'm glad you asked. A tetrahedron, first of all, it's kind of a tongue twister, I will say. This is one of a kind. This is one kind of a pyramid, which is polyhedron with a flat polygon base and a triangular face, connecting the base and so the triangular pyramid has basically 4 triangular faces, 6 straight edges, and 4 vertex corners. And that's kind of what that is. So in this problem, whenever we have to draw it, a cube with the vertices here that we have A, B, C, D, E, F, and G, and H is shown in the accompanying figure. The vertices D, E, G, and H are the vertices of the tetrahedron in the middle of the cube. And that's what's in red. So now when we construct that, it's basically your D, E, G, and H. So yeah, so it's pretty simple. You just kind of connect those lines, the D to the E, the E to the G, and finally to complete it, the G to the D.
Hey, Joni, I have a question.
Okay.
So when you place your tetrahedron in the cube, does it not touch any faces?
Does it not touch any faces?
Like it's not face to face?
Hang on. So, well, I'm not really sure. So, well, it's going to have 4 triangular faces.
How you position it inside the cube.
Yeah, it's going to have 4 triangular faces and 6 straight edges.
Correct.
So I'm not really sure if I understand exactly what you mean by that.
Okay. So what I'm saying is the way you have it positioned inside the cube, it's not touching any face of the cube at all.
Oh, you mean the front faces?
Yes, ma'am.
Correct.
Yeah. No, it's not. It's gonna go in the 4. It's gonna go in the corners, the 4 vertex corners.
Okay, I understand now. Thank you.
Yeah, I think it just all depends on the way that you position the tetrahedron inside.
Right. It's going to have 4 vertex corners and the convex polyhedrons, and they only have the 5 faces. So I don't know.
Right. So it could share a face with the cube, but it also could not. It all just depends on the way that it's positioned or drawn in there.
Right.
Okay. Thank you.
And kind of how you look at it. So. All right, so this is the doubling system. And so we were asked to find how many mouthfuls are in a gill, a cup, and a pint. But before we can get to that, we need to understand how a doubling system works and kind of what it consists of. And so the easiest way to do that is to look at all of our measurements by the smallest quantity. And in this case, our smallest quantity is a mouthful. And so a mouthful is obviously equal to itself. So one mouthful is one mouthful. So I don't need to show that. And so then we go up to jigger, which is 2 mouthfuls. So it is going to be double what just 1 mouthful is. So we're doubling 1 and going to 2 for a jigger. And so to go up to the next value in the measurement system, we're going to double that. And so it's going to go from 2 to 4. And I bet you can probably guess what it's going to go to next. 8. The gill is going to be 8.
Double it.
Yep. And so to move up from there, you can multiply it by 2. You're going to go to 16. And so a cup is going to be 16. You're going to multiply it by 2 again, and you're going to go up to 32, which is a pint. And so to answer the question, how many mouthfuls are in a gill, we have 8. A cup is 16, and a pint is 32. And so the second part of that question was if we added one of each measurement smaller than a pail into a pail, would it overflow, fill up perfectly, or would there be room for more? And so in order to do this adequately, you need to break everything down to the smallest measurement, which is a mouthful, because a mouthful can't be measured by a pail. It just wouldn't work. And so when we look at all of these, you'll notice that it goes from 2 to 4 to 8, 16, 32 is a doubling system. And so when we look over here, we look at our pail, which is the largest. After we have doubled all of these and gone down the whole way, we see that it's 512. And so when you're multiplying to go up, you divide to go down. So divided by 2, so we know that a gallon is 256, 128, 64, 32. And so if we know that there's 512 mouthfuls in a pail, in order to see if we added them all together, if there would be room for more, we just simply add them all together by the mouthful, because again, you have to go by the smallest quantity, because you can't say that a mouthful is 1/512th of a pail. It wouldn't work. And so when you add them all together, you get 511. So there is room for more, and there is room for 1 more mouthful.
Oh, wow. That was a mouthful, I have to say.
It really was.
And you definitely have to know your 2 multiplication tables.
Mm-hmm.
If you don't know your 2s, you're pretty much not going to know how to do that problem.
Well, if they can multiply by 2 or add it together, you don't necessarily have to say 256 times 2. You can just have children who can't multiply quite that well, 256 plus 256. So adding it to itself, it might make it a little bit easier for younger kids.
Yeah.
That's right.
Yeah.
Okay, so in this lesson, we're going to go over how to find area and perimeter for a certain shape. Okay, so let's look at this shape. So this is a triangle, and there's 48 meters, 69 meters, and then 82.3 meters. So the formula to find area is A equals 1/2 BH. And then we're going to plug into our numbers. So base times height, so base is 82.3 meters, and then multiply by height with it, which is, I meant to put 48.0, and then you get those and you multiply them by each other, and then you get the area of 1,687.5 meters squared. Don't forget to put the meter squared, because sometimes I do. So now we're going to figure out how to find perimeter. And perimeter is the distance around any shape or figure, so all you have to do is just add up your sides. So 82.3 meters plus 48 meters plus 69 meters. And then we get the answer of 199.3 meters. And that is how you find area and perimeter for this shape.
So Gabby, why don't you include the 41 meters that's right here into your perimeter calculations?
Okay, that is because, so perimeter is the outside of a figure, and it's just surrounding the shape. So you can add up all your sides, but since 41 meters is on the inside, you can't add that. It's just kind of explaining the height in the middle of that shape, if that makes sense.
Okay. So you would use this for the height formula for area.
Yes, exactly.
Okay.
Yes. Okay, next we're going to do the same exact thing, same exact method. So we need to know the formula for area, which is A equals B times H. And then we're going to just plug in our numbers. So we're going to have 1/2 times B times H. So it would be, the base would be 88.8, and then the height would be 37 inches. And then we multiply those, and then we get 1,642.8 inches squared. Then we're going to do the same exact thing with perimeter again, and we're just going to add up all of our sides. So we're going to do 88.8 inches plus 38 plus 96.3 inches. And then, so there's a mistake on this one. It says that the perimeter is 8 point something, but I went back and I used my calculator, and it's actually 223.1 inches squared. So that's how you find perimeter for that one.
Okay.
Okay, and then we're going to do the same exact thing. So we're going to plug in our area formula, which is A equals 1/2 B times H. Then plug our numbers into it, and then we're going to get A equals 1/2 multiplied by 6.2 centimeters by 2.6 centimeters. And then we're going to get the area of 8.06 inches squared. And then next we're going to do perimeter again. So let's add all the outside numbers. We're going to do 6.2 plus 3.1, and then you get the area of 8.5 centimeters.
Hey, Gabby, why
Yes.
wouldn't you use the 3.1 as your height when you're finding area?
Let me look. So 6.2. Are you talking about how you didn't add, like I didn't add height in the
Why didn't you use the 3.1 and you used the 2.6 instead?
that is showing, the 3.1 centimeters is showing the distance between that. The height is just going to represent the length of the figure. So that's why we have to add the 2.6 for the height.
Right.
Kind of
So this is like at a diagonal. This is the side. So if you were to look at this at height and stand it up, it'd be way up here. And this is just actual height of the figure.
Mm-hmm.
Okay. Thank you for explaining that.
No problem.
Okay, so this one is our next one. It's lesson 3, problem 3, and it asks us about a square with sides of the length of 10 units is inscribed in a circle around another circle, which is larger in the area of the region between the circles or area inside the smaller circles. So it's wanting us to find out what is inside, what is the area inside the bigger and the smaller circle. So when we do this, the equation for the area of circle is going to be your pi radius squared. So the area of the region between the circles is the area of the circle minus the area of the smaller circle. So to find the area of the two circles, the square's side length is 10 is the same diameter of the small one. So this means the smaller radius is going to be 5. So when we find the area of the smaller circle, we are going to do your area equals pi r squared. And you're going to plug your 5 in because that's going to be your 5. That's going to be half of the 10. And you're going to get your 25 pi. So to find the larger circle that has a radius equal to half of the diagonal of the square, to find the radius of that, you're going to have to use the Pythagorean theorem. So the Pythagorean theorem, it says that if a right triangle has legs of length of A and B and the hypotenuse has a length of C, basically your formula for that is going to be your a squared plus b squared equals c squared. So in this, we're going to plug in our 5 and we're going to solve. So we're going to put 5 squared plus 5 squared, and which equals our 50r squared. So now we're going to find the area of the larger circle. So we're going to substitute that 50r squared, and the formula for that is going to be your pi r squared. So that's going to be your 50 pi units squared. So now we're going to subtract the area of the smaller from the larger. So when we do that, you know, it's simply going to be your 25. So the smaller circle and the region between the circles both have the area of 25 units squared. Anyway, that's a lot.
So they're equal to each other. They're the same.
Well, they're the smaller circle, yeah, they're going to be
like the area in between.
Right. Yes. Yes.
Okay. And
that is
so
a lot. That was a lot. Do what?
So when you use the Pythagorean theorem to find the area of the larger square, and you cut this on the diagonal, did you basically do kind of what Gabby did a little bit, and like this side would be A, B, and then the diagonal would be your C, which is your radius squared?
Right. If you look at your square in there, you can see your right triangle.
Right.
And so then you just kind of cut in between in the middle.
So you cut it in half and you use
right.
that triangle to find the area.
Yes.
Okay.
All
that
right.
was a lot.
I know.
All right, everybody. So right now we're going to be looking at a figure that's going to pop up, and that's going to be what we're going to be working on. We're going to look at the surface area on how to find it for this figure, and we're going to look at the volume on how to find it. So we have this cylinder that's popped up, but attached to it at the very top, we're going to have this cone. And so when we have two shapes come together to make one figure, that means that we're needing to take the equations of both of those shapes, the cone and the cylinder, and add those together to find the surface area and the volume. So if you look in the yellow box up at the very top, it's going to give you that for you. So you have the surface area equals pi r squared plus pi rs plus 2 pi rh. And so we know that r is going to be the radius. We know h is going to be the height. And so when we plug this together, we're going to figure out what that is. And so that S right there, that is going to be a side of the cone.
Sorry.
You're okay. So when we do that, we're going to plug it in to get pi 2 squared, because that's going to be the radius of that cylinder and the cone, plus pi times 2 times 6 plus 2. And that's going to add up when we get done with it to be 176 m squared. We come to this conclusion for the volume of a cylinder. When we look at the equation that we have pi r squared h1. That means the height 1 for the cylinder. And then for the cone, that equation is going to be 1/3 base times height. And I put h2 because we're going to need to know the height of that cone. So we have two heights to worry about. But as you can tell, we don't know the height of the cone. We just know the side length. So in that blue box, it says h2 equals what? So what you're going to do is you're going to put 6 squared minus 2 squared. And that's because the 6 is coming from the side of the cone and the 2 is coming from the radius. But when we solve that for the square unit, it's going to be 5.7. And we're going to use that to plug in for our height too. So just like before, we're going to plug in our numbers. So b equals pi 2 squared. And then we're going to do our height 1, which is 10 of the cylinder. plus 1/3 pi, 2 for the radius squared, and then our 5.7. And when we do that, we're going to get the volume of 150 m cubed. Now, it's very important to recognize that in volumes, you're going to have a measurement of cube. And in surface area, you're going to have it squared. And so you need to be able to remember that as we go on to our next problem. Thank you. So again, this problem is going to have surface area and volume. And as we saw just now, we see that this cylinder has a half of a circle cut in half and applied to each end. So that means that we're going to have the same equation for a sphere and cylinder put together for the volume and the surface area. So if we go and look at our green box, we see that the surface area equation is going to be 2 pi RH plus 2 pi r squared. And so we know that our diameter is going to be 8 feet. And we know that if we take half of that, that is going to become our radius. So that's going to be 4. So when we plug that in, we're going to get 2 pi times 4 times 21 because it's the height of the figure, plus 4 pi times 4 squared. When we do that and solve, we'll get a surface area of 729 feet squared. And so now we're going to go ahead and move on to the volume. And the volume is going to be 4/3 pi r cubed because of the circle or of the volume plus pi r squared h. So we know that we can go ahead and get that situated with our plugins. So we can go ahead and do 4/3 pi, plug in our 4 for the radius and cube it. And then we're going to add pi, put the radius in 4 squared and the height of 21. And when we solve that, we're going to get a volume of 1,324 feet cubed. I want to go ahead and remind you again, the volumes is in cubes and surface area is in square units. And so that just is very important for us to remember.
So is volume always going to be cubed?
Volume is always going to be cubed. Yes, Callie. And that's because it's like a 3D figure. You're filling up the whole figure to all the space filled in.
Okay. And so your surface area is always going to be squared?
Yes, it is.
Awesome. Thank you.
You're welcome.
Now we're going to get into lesson 4, kicked off by Gabby.
Okay, so today we're going to go over what shapes are symmetrical. So first, let's go over what it means to be symmetrical. So I think the easiest way to explain it is, let's say you cut a straight line down the middle of every figure, okay? Let's say you have a piece of paper. If you were to flip it over and fold it, if every single side meets evenly and they are perfectly exact, then they're symmetrical. But if you were to fold the figure over and one side is overlapping or they're not matching corners, then it's not going to be symmetrical. So over here, we're going to add some lines in the middle to kind of represent what it could be and what it could look like. And see how these are going down the middle and how some of these can be symmetrical and some of these cannot. So let's look at let's look at the rectangle, for instance. That reminds me of a piece of paper. So there's a cut down the middle. If you were to fold it and meet sides, it would be exactly the same. They would look exactly the same. So that's how you know it's symmetrical. Now let's say the third shape, for instance, that's not symmetrical. If you were to cut it in half, it would not be even. You could not fold it evenly. It's just like closing and opening a book. Like if it's not going to meet, then it's not symmetrical.
So would this shape right here, the very first one, be symmetrical?
No, that would not. If you were to flip that, it would not meet edges, so that would not be symmetrical.
So that one's not, and then the third one wouldn't be symmetrical, but all the other ones are symmetrical?
Yes, they're all symmetrical. Okay, now we're going to determine if the shapes meet the standards to have one line of symmetry and also rotational symmetry. So each one I go over, we're going to talk about if they meet the standards or not. So let's look at this first one. So this does not have a line of symmetry, as you can tell, like we looked at the last example, but it does have rotational symmetry. Now let's go over rotational symmetry. If you were to rotate the figure, and let's say we rotate it 180 degrees. If it looks exactly like the original shape, then it has rotational symmetry. But if you were to rotate another shape 180 degrees and it looks completely different, or it's in a different position, then it does not have rotational symmetry. Okay, so now let's look at the next figure. So this diamond shape has rotational symmetry, but it has 4 lines of symmetry. So that does not meet all standards. And then the next one, this one doesn't have a line of symmetry, but also it does have rotational symmetry. Then the triangle, this has a line of symmetry, but it does not have rotational symmetry. And then next, the last figure, this has rotational symmetry, but has 4 lines of symmetry. So none of these have met the standards of 1 line of symmetry and rotational symmetry. But I actually do know what shape could in fact meet the standards, and that would be an isosceles triangle, because it has 1 line of symmetry and also rotational symmetry.
So Gabby, for this right here, the reason why the diamond and the triangle below, or not the triangle, but the diamond and the rectangle does not meet the standards is because it has more than 1 line of symmetry?
Exactly. So you can cut these into fourths and they would be exactly the same. That's how you know it has different lines of symmetry, because you can fold them and cut them certain ways, they'd be exactly the same. They'd all like come to little triangles or something. So that's why that does not meet the standards.
Thank you.
You're welcome. And then next, we're going to go over just what we talked about. We're going to go over rotational symmetry. So we're going to look at the original shape. So just look at these shapes, and then we're going to rotate it 90 degrees and then 180 degrees. So let's look. So let's look at every shape. We took these out from the last slide, and we found out which ones had rotational symmetry, which were all these, because let's look at them in a 90-degree rotation and then a 180-degree rotation. If you look at the 180 degrees, they look exactly like the same original point. They are in the same position, same size, same shape, same everything. So that's how we know that all of these have rotational symmetry.
So all of them have rotational symmetry?
Yes. All of these shapes listed have rotational symmetry.
Okay, so we are going to go over lesson 4, number 3. So we're going to figure out, when Myra cut out our regular pentagon, hexagon, and octagon, and it seems to her that they form a vertex figure. Let's figure this out. So first of all, what you need to know, any arrangement of non-overlapping polygonal tiles surrounding a common vertex is called a vertex figure. But the thing that we have to know about that is the measurements of that. The measurements of the interior angles meeting at a vertex figure must add up to 360 degrees. So on this, her first one is 108 degrees, and then she has 120 and 135. So what we have to do to figure this problem out is basically we just have to add all those up. It's just very simple. So we're going to add those up, and it is 363 degrees. So this one is not going to be a vertex figure because it is over the 360 degrees. Now, if, say, that pentagon was 105, then we would have made it. But it wasn't. It went over the limit. So it is actually going to be it's not going to be a vertex figure in this one. So that's what we figured out with this problem.
So you could kind of connect this with a previous problem we did where we found the measurement of these interior angles.
Mm-hmm.
And you could add those up to see if they're 360?
Yes. And if they're not, then they're not going to be the vertex figure.
Right. So only where they meet up. So like this spot right here, I don't know if you can see me circling it. That's where they need to equal 360.
Yes.
Okay.
All right, guys. So we have this line M, and we see all these things popping up, and we're going to look at each individual one of these. So the first thing that popped up was that line M, and what we want to know is all these triangles that are on this line similar and congruent, and how do we know those? Okay, so in this line M, we can see that we are going to look at these blue lines that are connected. So we have Q to P, that blue line that we're looking at, and S to P that we're looking at. And we know that that line right down the middle is kind of like a cookie cutter, right down the middle of a cake. And so that means that PPB is going to be the same measurement as SPB. So they're going to be congruent, because their length right there are going to be the same. Now, when we look at the yellow lines, the QTB and STB triangles or lines are going to be congruent because they're at the same points as the previous blue ones. And also because of that line right down the middle, it's demonstrating to us that those two lines are going to be congruent. Now, since these lines are congruent, that's going to mean our triangles that they make are congruent. So if we look at the QPT, the big one, and the SPT, those are also going to be one solid triangle. And since we know that those sides are congruent, that is going to make those from side, theorem. Those are going to mean that those are congruent and similar triangles.
You always do such a good job of explaining.
I
You
try.
really do.
Thank you for explaining that, because I would have never been able to explain it like that.
You're very welcome. I appreciate it, y'all. I do. Oh, and then the right angle, of course. Yeah, sorry. We know that the right angle right there of the QVP, because, of course, the lines are going up and down, and the line is 180 degrees, and when it's cut in half, it gives you 90 degrees.
All right, so this is a long one. Sit back, get ready. So we were asked to find angle NOQ. And so we can see, here's angle NOQ, it is in blue. And when you look a little bit closer, you see that it is the space in between angle PON and POQ. It's kind of the void space in the middle. So first thing we need to do is find angle PON. And if you look really close, you can see the angle PON is in the pentagon labeled penta, P-E-N-T and A. And we see that it is two central angles, because the central angle is from one side to the middle to the next. And so this is equivalent to 2. And so to find the measurements of that, we would need to find a central angle. So to find a central angle, you would take 360 divided by 5, which is the number of sides for a pentagon. And we can see that one central angle for the pentagon is 72 degrees. So you multiply that by 2 because angle PON is the equivalent of 2, and we know that it's 144 degrees. So angle PON is equal to 144 degrees. So then we can see that inside the circle, but not inside penta, we have equilateral triangle PQR. And so we can see that angle POQ is one central angle of our equilateral triangle PQR. So we would need to do the exact same thing and find the measurement of that central angle. And so to do that, you would take 360 and divide it by 3, which is the number of sides of the equilateral triangle, and we get 120. And so because we know that this is the space in between, this is the difference in angle POQ and PON. When you hear the word difference, you know you're going to subtract. So we are going to subtract 144, which is the degrees of angle PON, and we're going to subtract angle POQ from that, which is 120. So we know that the angle of NOQ, which is the space in between, is 24 degrees. I know that was
Charlie.
y'all all comfortable with that?
Yes, I
Yes.
like how you explained it and told us that when it's the different space that we're going to be subtracting it. So that helps
Right.
me a lot right there.
Yeah.
It was a lot of steps to get to the one angle, but completely
Okay.
doable.
All right, guys, did you miss me? I'm back. All right, so we're going to be looking at trying to find the height of the cliff that Jenny is looking at. So Jenny has a ruler held out in front of her at 2 feet. And the top and bottom of that cliff is separated by the mark 1.5 inches. So, and we know that Jenny is a quarter of a mile from the cliff. All right. So let's look at the hint. The hint on 1 mile equals 5,280 feet. So to find out what a quarter of a mile is, you do 5,280 feet and divide it by 4, which will give you 1,320 feet. And now we have to convert the inches into feet. So we're going to take 1.5 and divide that by 12, since there are 12 inches in a foot, which will give you 0.125 feet. So now we're going to put it into an equation. So 1.5 or 0.125 feet over 2 feet equals the height of the cliff over 1,320 feet. So you're going to multiply 1,320 feet by both sides. So it'll leave you with the height of the cliff equals 0.125 feet times 1,320 feet over 2 feet, which will give you 165 feet over 2. And when you divide that by 2, you will get 82.5, but when you round it, it'll give you 83 feet for the height of that cliff.
Cheyenne, I have a question.
Yes, ma'am.
Okay, so the reason why you broke down everything, like the miles and the feet, was because you have to have the same common measurement to be able to do your multiplication in this problem, correct?
Yes, because it would be hard to do if you're trying to do it with inches, because like say, because when you're looking at a cliff, you don't want to measurement in inches, because that's a lot of inches. So when you convert it into feet, it's easier to tell, instead of looking at somebody that says, oh, well, you're 54 inches tall. Really, you're like 4'7" feet tall. It's easier to say that instead of having to do it in inches.
Thank you.
You're welcome.
Kind of like a common denominator in between miles and inches.
Yes.
Right.
Good job.
Good job.
Thank you.
All right. Thank y'all for watching, and I hope you learned a lot from this wonderful team. We saw lots of bases and all kinds of crazy things. So thank you so much. I'm Joni Overly.
Calie Plummer.
Gabrielle Guest.
Amanda
Calie
Pennington.
McDorman.
And we hope y'all had a great day. Goodbye.
Thank you.
Bye.